Here we go. We're done with learning straight up programming concepts and new stuff, and we're basically moving on to the last three modules of the class, which um, are what I would consider to be just fun projects that we can work on. In it, you're going to learn how to do work with images. You'll learn how to build a graphical user interface, and you'll learn the very basics of designing a game with Python. So those are a little more fun. They do use a lot of the advanced concepts that we've been talking about the last few weeks. So it's not like they're overly simple, but I do think they're a little bit more fun in that you get to sort of use your imagination and play around a little bit more. So this module, module 16, involves image processing using a library for Python called Pillow, which is short for Python Image Library, or PIL. And Pillow is one of many image processing libraries, but it's also very common. I would consider it the most common of the image processing libraries, and it does a good job, and it's compatible with some other things that we want to do. So Pillow is a nice skill to have under your belt for a lot of reasons. So Pillow works with images, and in order to do work with images, you have to understand a little bit about how images are built or how computers look at images. So I'm going to give you some basics today, and I'll give you a few more basics on Wednesday as to how images are represented using data. Because obviously everything in a computer, even images, are represented using numbers. And so understanding how those numbers represent the image data so that it can be recreated on our screen is really an important thing when we're talking about editing images and changing images. The first and most important thing you need to know about images is that every image, no matter what it looks like, no matter how high resolution or how low resolution, or if it's a GIF or a JPEG or a PNG or any other image file, all images are made up of what are called pixels. And I'm not talking about little fairies. Those are pixies. I'm talking about small squares. And yes, they are squares. They're not dots. Each little square pixel, because of the way screens are represented, often using what are called liquid crystal displays, pixels are most easily formed in squares rather than dots. Also, if I put a bunch of dots next to each other, round ones, there's always a lot of blank space that they leave. This squares can be put together seamlessly and cover the whole screen. So that's kind of some of the reasons why pixels are squares. Each pixel on every screen in every image is represented by at least three numbers. Now, those three numbers, sometimes there are more numbers that represent other data having to do with that pixel, but each pixel has at least three numbers associated with it, representing the varying levels of red, green, and blue light. So each pixel can have one of many colors. Each pixel has a value for red, let's say, that is between 0 and 255. Same for green and blue. So the number of colors that we can make using 256 different color values for red, green, and blue is equal to 256 times 256 times 256, which is in the millions, the tens of millions, actually. So we'll get down to exactly how many colors on Wednesday, but it's a lot. It's a lot unless we compare it to the number of colors our eyes can actually see, because our eyes can actually see 10 times that maybe. So it still is limited. And these days, our screens are so high quality that we have forgotten that pixels even exist because we can't really see them. Sometimes if you get a magnifying glass or you get really close to your screen, you can see them, yes?
I have a TV that you could still see the pixels.
Now, a TV, is it a CRT, a television, or is it just an old LCD? Is it flat screen?
No, it's a box.
It's a box. Okay, so those are called a cathode ray tube. And those actually project, they actually, inside them, have red, green, and blue projectors that overlap each other. So that's, in the really, really olden days, you used to actually have to align those three projectors. They could get out of alignment, and you would get red, green, or blue, like ghosting around images and things like that on the screen. Those are really old. In fact, the first color television sets would always boast that they were RGB color, right? Red, green, and blue. So that's where we get that from. And the reason that we chose those colors, and you might be saying, whoa, those aren't primary colors. Primary colors are, what color is wrong here if I'm looking for primary colors? Green, right? Because we've all been taught since like preschool that green happens when you combine yellow and blue, right? Those are the yellow, blue, and red are the primary colors. That's true if we're talking about pigments or ink. In light, when we're talking about lights, it's a different color model. And these are actually the primary colors when we're talking about lights. It's called an additive color model, in which the full strength, if we have 255 times 255 times 255, full strength of all three of those makes white. And if we have the right shades of green, red, and blue, at full strength, we will have white light. And that is the color model. The absence of all of these, obviously, is black. Now, in a subtractive color model, when we're using ink, if I give full yellow, full blue, full red, I will get close to black. Now, we can't get true black using those three, which is why printers often use a different color model. It's called CMYK, cyan, magenta, yellow, and black. Now, all of these things are connected because they actually are just sort of looking at the opposite side of the coin. But the most important thing we need to know is that every image is made up of dots that has three numbers that tell us red, green, and blue. Why is that important? Because all we're doing when we change images is just changing those three numbers for each pixel. If we do it intelligently, we can get some pretty cool effects.